to Auntie Aje's chemistry class. I thank you for subscribing to this channel. And in case you have not subscribed to this channel, tap on the subscribe button and turn on the notification bell. Please don't forget to like and share the video. Today, we are going to look at the simplest way of writing electronic configuration, which I term writing the electronic configuration of elements using quantum numbers. In case you have not heard about quantum numbers, don't be disturbed about that. So I'm going to use just 2 out of the 4 quantum numbers to teach you how to write electronic configuration. Now let's look at the first quantum number that we will use in writing this electronic configuration, known as the principal quantum number. Principal quantum number, represented by the symbol n. The principal quantum number is represented by the symbol n. And what does it talk about? It talks about the main energy level, known as shells. The principal quantum number talks about shells, which are referred to as main energy level. This principal quantum number gives these shells symbols. The symbols for the shells given by the principal quantum number are as follows: K for the first shell, L for the second shell, M for the third shell, and N for the fourth shell. In that case, principal quantum number N, value of N, principal quantum number for the shells, is as follows: K has the value of 1, L has the value of 2, M the value of 3, and N has the value of 4. Now, according to this principal quantum number, if you go by what we already know in the shells, sorry, let me clean this and write 4 properly so that you can see it very well. If you go by what you know about the shells, what you have been taught about the shells, we have that the shells are the shells of an atom of elements are usually written or usually drawn in circular form, where you have the first shell, K shell, shell number 1. We have the second shell, L shell, shell number 2. We have the third shell, M shell, shell number 3. And we have the fourth shell, M shell, shell number 4. That's what I've just represented on the board. Now let's go to the second quantum number, which we call the subsidiary or azimuthal quantum number. Azimuthal quantum number or subsidiary quantum number. Now, this subsidiary quantum number describes the sub-energy level. Sub-energy level, referred to as orbitals. And this quantum number is represented or denoted by the symbol L. Symbol L stands for the subsidiary quantum number. Now, this quantum number describes the orbitals which are given these symbols S, P, D, F. So we have 4 orbitals: S, P, D, orbitals. Now this subsidiary quantum number says that the maximum number of electrons for each orbital is given as 2 for s orbital. P can contain maximum of 6 electrons, and D can contain maximum of 10 electrons, and then for beta will contain maximum of 14 electrons. If you look at it, you see that we started with 2 and we're adding 4. 4 to 2 will give you 6, 4 plus 6 will give you 10, and 4 plus 10 will give you 14. Now, how do we make use of this to write electronic configuration? See, very, very simple. Start with the shells. You put the shells K, L, M, N, and then give them their numbers 1, 2, 3, 4, and then bring in the subsidiary quantum number. Now, the principal quantum number says that the K shell has number 1 as its number, L number 2, M number 3, and N 4. But the subsidiary says that the number of number of orbitals in each shell is as follows. For K shell, so we say number of orbitals. For K shell, it has only 1 orbital, denoted by the number 1, s orbital. For L shell, it has 2 orbitals, s and p. For M shell, it has 3 orbitals, s, p, d. For N shell, it has 4 orbitals, s, p, d, f. So we can now combine to get 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, and 4f. So assuming you were asked to write the electronic configuration of an element given by the symbol, X, with mass number 24 and atomic number 12. Now, when you want to write electronic configuration of elements, if you are given this kind of symbol, you use the number down, which is the atomic number. And remember in the last video we said atomic number represents the number of protons. And in a neutral atom, the number of protons equals the number of electrons. So we assume that 12 is the number of electrons. So let's write the electronic configuration using this. So we come back to write the electronic configuration of S using 1s2. Don't forget that here the maximum number of electrons in s orbital will be 2. So we have 12 electrons, we fill in 2. And then we go to the second one, we say 2s, we fill in 2 again because it's an s orbital, and we are filling 4 electrons, remaining 8. We move to the next one, 2p, 6. We take up 6 out of the 8, remaining 2. And then we move on to say 3s2, and that makes it 12. 2 plus 6, 8, plus 2, 10, plus 2, 12. We have written the electronic configuration of the element X. Now finally, let me just do one more problem for you. If you are given an element with the symbol T, and you are given 17 here, and probably 35.5. From what we have done, you know you are going to use 17 to write the electronic configuration. So how do we do that? We will move in from here. Let's go straight from here. We say 1 plus s 1 joined to S, we have 1s. We put in 2 electrons. Let's move to this place. We now say 2 joined to S, we say 2s. We put in another 2 electrons. We say 2 joined to P, we say 2p. We put in 6. You know why we're putting in 6? Because we have more than 6 electrons still remaining. And P takes a maximum of 6 electrons. And then we go to the next one, 3. We go to the third shell. To fill the third shell, we say 3s2. And how many electrons have we filled so far? We have filled 8, 10, 12. Remaining 5 out of the 17. We move over to the next one, 3p. And how many electrons are we going to fill? Normally it takes a maximum of 6, but we don't have up to 6 remaining. What we have remaining is just 5 electrons. We fill in the 5 electrons. And we have written the electronic configuration of T. This is where we're going to stop for today. Don't forget to like the video and share the video. Thank you.